This is the Algebra 1 Summer School Unit 7 Lesson 4 Notes video. Lesson 4 is all about quadratic modeling. Alright, quadratic equations pop up in many real-world situations. We're going to work with examples where we will use both the vertex of the parabola and the solutions. Remember, solutions are the x-intercepts to tell us what is happening in context of the real-world problem. For example, a lot of our situations are going to talk about projectiles. When you throw or hit a ball or shoot an arrow, fire a missile, throw a stone, etc., it goes up into the air. So say you're this person. You have a ball in your hand. When you throw it, it goes up into the air, slowing as it goes up, and then it starts coming back down towards the ground. The shape it makes is a parabola. The quadratic equation for that parabola tells you the position of that object at all times. So example 1, we're going to start with a graph that's already made for us. It says the graph shows the height in feet of a small rocket t seconds after it was launched. The path of the rocket is given by h equals negative 16t squared plus 128t. Don't forget to include units with every answer when we use any kind of modeling, linear, exponential, or quadratic. We have to include units to make it mean something. So A, how long was the rocket in the air? Well, it seems that my rocket was launched over here. It travels up, it comes back down, and then it hits the ground. That amount of time looks like it was 8 seconds. So the rocket is in the air for 8 seconds. Next, what is the greatest height the rocket reached? Well, this is at the vertex. The height that goes with that, it's not 250, it's one tick above that, which looks like it's 260 feet. Now, how high is the rocket after 1 second? So go to 1 second here, go up my graph, and it appears to cross right about here, which looks like it's at 110 feet. So it's about 110 feet in the air after a second. Now after 2 seconds, how high is the rocket? So go to 2 seconds, I go up to the graph, there's that, and I go over to my scale, and I'm about 190 feet in the air. After 2 seconds, is the rocket going up or down? Well, it looks like the rocket's on that upward trajectory. That's a hard word to say, so it's going up. All right, let's look at the next part here. After 6 seconds, about how high is the rocket? So now this time I'm going to go to 6 seconds, go up to my graph, and it looks like my rocket is again at about 190 feet. But this time after 6 seconds, that's when the rocket is going down. Now, do you think that the rocket is traveling faster from 0 to 1 seconds, so from 0 to 1 right there, or from 3 to 4 seconds, which is this portion of the graph right there? I would say that it's traveling faster from 0 to 1 second because the graph down here is steeper than the graph at the top from 3 to 4 seconds, and steeper means faster. So I would say the graph is steeper here. Steeper means faster when we're doing word problems. Finally, using the equation, find the exact value of the height of the rocket after 2 seconds. We approximated that height up here at about 190. Now we're going to use the equation to find the actual height. So we're going to say h equals negative 16. The time is 2, so 2 squared plus 128 times 2. All right, when we put that in our calculator, we end up finding out that the rocket is actually 192 feet high. So we were very, very close with our approximation. All right, so sometimes when we do quadratic modeling, we're going to give you the graph. And when I give you the graph, it's pretty easy to figure out some of the information. When does it hit the ground? How high is the rocket? Sometimes you're only going to be given an equation like this OST question. It says a grasshopper jumps off of a tree stump. The height in feet of the grasshopper above the ground after 2 seconds is modeled by this function, negative t squared plus 4/3 t plus 1 over 4. After how many seconds will the grasshopper land on the ground? Well, let's draw a little picture here, just so we can see what's happening. So we have a grasshopper. The grasshopper is jumping. Eventually, it's got to hit the ground. When I think about this in terms of a graph, hitting the ground is the x-intercept. Where does the grasshopper hit the graph again? So you need to have a graphing calculator in order to complete this problem. To find where it hits the ground, I'm going to graph this equation in my calculator. So I'm going to type in, instead of t, negative x squared plus 4/3, so I'm going to use my parentheses here for the fraction, plus fraction 1/4. When I graph this, there's my parabola. It's tiny, but I can still see it. My goal is to figure out what this value is right here. When do I cross the axis? Right there. That's where I hit the ground. I start here, I jump, and then I hit the ground. Your calculator can do that work for you. What you're going to do is you're going to go to second trace. Now you're going to go down to 0, because on our calculator, remember, zeros. We learned were x-intercepts, roots, and solutions. Those are all the same thing. So we're going to choose 0 because it's going to find us the x-intercept. So let's go down to number 2 and hit enter. You should see a flashing cursor. It says left bound. So I want to take that cursor just to the left of this root. See how I'm to the left of the root here. So I hit enter, and then it says right bound. So I take the cursor to the right of that x-intercept, which is just a little bit below the axis. I hit enter again. Now I want to guess and hit enter one more time. And it tells me that that x-intercept is at 1.5, 0. So what that means is that, this grasshopper hits the ground after 1.5 seconds. Go. That's it. That's all there is to that problem. All right, next one here. Example 3. A golf ball is hit from the top of a roof. Its height in feet above the ground after t seconds is given using this equation. Negative 16 times t minus 2 squared plus 144. It says using your graphing calculator, graph the parabola. Adjust your window so you can see the whole graph. All right, I need to help you with that. So let's go back to our graphing calculator. Right? I'm going to have to erase some of my writing here. Now I'm going to graph this equation in the y equals here. Now, so I'm going to have negative 16 parentheses x minus 2 squared plus 144. When I hit graph, you're going to see really quickly that you don't see most of the parabola. You see part of it, but you don't see all of it. We're going to adjust our window. And we're going to adjust our window based on what the scale is on our axis over here. So my y-axis is going to go from 0 to 150. And it looks like we go by tens. And my x-axis is going to go to 6 going by, or we'll go to 10, going by ones. So the way I adjust my window is I hit the window button. We said our x minimum was 0, and we're going to go up to 10 and go by ones. Now my y minimum, again, I'm starting at 0, but we said go up by 150. Again, remember, when I look here, my scale goes up to 150, and it's being counted by tens. So my y scale, the next one, is 10. This time, when I hit graph, I can see the entire graph. All right, now we can use this graph to help us answer some questions. That's the picture. Now I want you to go to your table, fill in the values on your grid, and then we'll come back together after I do the same. All right, now using our graph, it says, when is the ball at its highest point? So when is it at its highest point? Well, look here, that time mine happens to be after 2 seconds. Now I said, what is the height at that highest point? Well, hopefully you have this on your graphing calculator still. If I look at my table, after 2 seconds, I'm at 144 feet. When does the ball hit the ground? Well, you should have plotted the point here at 5, 0. That means after 5 seconds, the ball is going to hit the ground. Now, what's the height at t equals 1? All right, now it says there are 3 ways to tackle this. First is the table on your calculator. I can go to my table and identify that the height is 128 feet. Okay, so that's what I got. That's one way. Table. Let's try trace on our calculator. What that means is I can go to the graph, I can go to second trace, and go to value. This is my favorite. It's fast. Under value, number 1, I type in time equals 1 second. When I hit enter, it gives me the y value right here of 128. That's exactly what I wanted. So we know that the table and the trace give us the same thing. Or I can plug it into the equation. Now that's going to take a little bit more time. That's why if you have the trace or your calculator, you can make this really fast. I'm not going to do the equation. Finally, it says, what's the y-intercept? Well, the y-intercept is where you cross the y-axis, which is at 0, 80. What does that mean in context? Well, that is at 0 seconds, that's the height of the golf ball. Or in other words, that means that the golf ball was hit from 80 feet above the ground. So the golf ball was hit from a height of 80 feet. So about 8 feet above, 80 feet, 8 stories above the ground. All right, let's try one more. This is one more problem where we gave you the graph. A ball is thrown straight up from 3 meters above the ground. Has a velocity of 14 meters per second. This equation, negative 5t squared plus 14t plus 3, can be used to model the situation. When does the ball hit the ground? That's easy. Now look at the graph, find the x-intercept. That was after 3 seconds. At what height is the ball after 1 second? Well, I go to 1, I go up to the graph, and I see that it is 12 feet high. Where's the y-intercept? Well, if I look at the y-intercept here, that happens at 0, 3, and that means that's the height that the ball was thrown from. So the ball was thrown from a height of 3 meters. All right, next. Function notation. It's been a while. It says find f of 3. Remember that 3, that number in the parentheses, is an x value. So I go to where my graph, where my x-intercept is 3, and I find the output. Well, at 3, the output is 0. F of 3, the output is 0. So interpreting that in context, 3 is an x value, and the x-axis here is measuring time. So that means after 3 seconds, the output, y, is measuring height. So the ball is 0 feet high. So the ball is on the ground after 3 seconds. Now it says, use your graphing calculator to help you answer the following questions. The way you need to do this is you need to type that original equation into the y equals of your calculator. So let's go and do that. Y equals negative 5x squared plus 14x plus 3. Now let's adjust our window. Let's look again. It looks like our scale here goes on the x-axis from 0 to 4. So I'm going to go ahead and actually just keep the window from 0 to 10. That should be fine for us. The y-axis goes from 0 to 14. So I need to readjust this y scale to start at 0 and maximize. Let's go to, 14 here. And we're going to go by ones because that's what our scale on our paper is going by. This time when I hit graph, I can see the whole parabola. Now the question they're asking me, when's the ball at the highest point? I want to know the time I get to the highest point. So I need to trace the maximum on my calculator. I'm going to go second trace down to number 4, which is maximum. I need to find a left bounce, so I'm going to take my cursor, oops, it's a little too far, so we're to the left of the vertex. There's my cursor, so I need to get it to the left of that vertex, which it is now. I'm going to hit enter, go to the right of that vertex, hit enter again, and guess, enter one more time. All right, so look here. The maximum, the x value, the x-axis was measuring time. So the time I got to the maximum height is 1.4 seconds. So that's the answer here, 1.4 seconds. Then it says, what is the highest height that we got? Well, that's the y. The height is the y, 12.8 feet. Now, you can use your calculator for the next one. Find f of 2.5. That 2.5 is an x value. So just like we did on the last problem, I'm going to go to the trace. I'm going to find the value of 2.5. So I'm going to click enter on 1 and type in x equals 2.5. It takes me right there on the graph, and it tells me that the y value is 6.75. So f of 2.5 is 6.75, and that means after 2.5 seconds, the ball is 6.75 feet above the ground. All right. Now, last question should be easy. How many total seconds is the ball in the air? Well, if it hits the ground after 3 seconds, that's how long it is in the air. 3 seconds. All right, this is probably the most involved modeling that we've done throughout this unit, so it's really important that you try the practice. Go ahead to Canvas, print out the practice, try the problems. If you have questions, watch the video that's posted, look at the key, or come into office hours and ask for help.